Today we are going to learn about advanced imputation techniques in Pandas. This video will equip you with skills to implement sophisticated imputation techniques to enhance your data analysis workflows.
Welcome to our session on advanced imputation techniques in Pandas. Handling missing data is crucial for maintaining the integrity of your datasets. While basic imputation methods like mean or median substitution can be useful, they often fail to capture the complexity of real-world data. In this video, we'll explore advanced techniques that preserve valuable information and enhance your analytical capabilities. We will cover the use of Pandas fillna with complex strategies, leverage sklearn SimpleImputer with Pandas, and delve into multivariate imputation using iterative imputer. Additionally, we'll address handling categorical data, apply k-nearest neighbors for imputation, and explore using machine learning models to fill in gaps. By the end, you'll be able to evaluate these methods' effectiveness with visualizations, ensuring you choose the best approach for your specific data. In the world of data analysis, imputation refers to the process of replacing missing data with substituted values. Simple imputation methods, such as replacing missing values with the mean, median, or mode, are straightforward but can sometimes lead to biased analyses. These methods assume that the missing data are missing completely at random, MCAR, which is often not the case. Advanced imputation techniques, on the other hand, aim to preserve the data's underlying structure and variance. They help in reducing bias and improving the accuracy of your models. By understanding and implementing these advanced techniques, you can ensure that your analyses are more robust and reflective of true data patterns. Throughout this session, we'll examine why advanced imputation is often more suitable, particularly in datasets with complex interdependencies and missing patterns that may not be random.
Pandas fillna function is a versatile tool that allows you to fill missing data points in your data frame. While commonly used for simple replacements, it can also be applied with more complex strategies. For instance, forward fill and backward fill methods propagate the last valid observation forward or backward to fill gaps. Another approach is interpolation, which estimates missing values based on other available data points. Pandas supports several interpolation methods, such as linear, polynomial, and spline, each catering to different data characteristics. You can also write custom functions for fillna to address unique imputation needs. For example, you might create a function that fills missing values based on a rolling average or a conditional replacement strategy. By leveraging these advanced fillna capabilities, you can tailor imputation to better fit the nuances of your dataset, thus preserving its original data structure more effectively. The SimpleImputer class from sklearn is another powerful tool for imputing missing data. It provides a straightforward approach to replace missing values using a constant, mean, median, or most frequent value. To use SimpleImputer with Pandas, you must first import it from sklearn.impute. You can then create an instance of SimpleImputer, specifying your desired strategy, and fit it to your dataset using the fit_transform method. This works well for both numerical and categorical data, though categorical data often requires preprocessing to convert it into numerical forms, such as using one-hot encoding. For numerical data, the mean or median can be a good starting point, while for categorical data, the most frequent value is often used. Custom strategies can also be implemented by creating custom transformers that integrate with SimpleImputer. By seamlessly combining sklearn's imputation capabilities with Pandas, you can streamline your data preprocessing workflows and make your datasets more robust against missing data issues.
Iterative imputer from sklearn provides a multivariate approach to imputation, which can be particularly useful for handling missing data in datasets with complex interdependencies. Unlike simpler methods that treat each feature independently, iterative imputer models each feature with missing values as a function of other features. This allows it to capture more nuanced relationships and dependencies within the data. The process involves multiple iterations, where each feature's missing values are imputed in turn, using a model that predicts the missing values based on other available features. Common models used in this iterative process include Bayesian ridge, decision trees, or random forests. Iterative imputer continues until the results converge, providing a robust and sophisticated imputation solution. This method is especially beneficial for datasets where variables are highly correlated, helping to maintain the multivariate distribution of the data. However, it's computationally more intensive, so it's essential to weigh its benefits against potential performance trade-offs. Imputing missing values in categorical data presents unique challenges compared to numerical data. One common approach is to replace missing values with the most frequent category, which can be efficiently done using sklearn's SimpleImputer with the most frequent strategy. However, this method might not always capture the complexity of the categorical relationships. To enhance imputation, you can combine this with encoding techniques such as one-hot encoding or ordinal encoding. One-hot encoding is particularly useful because it allows each category to be represented as a distinct binary column, preserving the categorical nature of variables. For ordinal data, where categories have a meaningful order, ordinal encoding is more appropriate. These encoding methods can also be combined with other advanced techniques, such as iterative imputer or k-nearest neighbors, to further improve imputation accuracy. By understanding and applying these strategies, you can effectively manage missing values in categorical datasets, maintaining their integrity for analysis.
K-nearest neighbors, KNN, is an effective imputation technique that uses the similarity between data points to estimate missing values. The basic idea is to identify k-nearest neighbors of a data point with missing values, based on a chosen distance metric like Euclidean or Manhattan distance. The missing values are then imputed using the average or majority value from these neighbors. Selecting the right k is critical, as too small a k might lead to overfitting, while too large a k may oversimplify the imputation. KNN is particularly useful in high-dimensional datasets due to its non-parametric nature, which doesn't assume any underlying data distribution. However, it can be computationally intensive and sensitive to outliers. Understanding these pros and cons is essential when deciding whether KNN is the right imputation technique for your dataset. By leveraging KNN, you can achieve more accurate and contextually relevant imputations, especially in datasets where data points have natural groupings or clusters.
Machine learning models offer a powerful alternative for imputing missing data by leveraging patterns within the data itself. Model-based imputation can capture complex interactions and dependencies better than traditional methods. Common models used for this purpose include decision trees, random forests, and gradient boosting machines, which are capable of handling both continuous and categorical data. The process involves training a model on the observed data and using it to predict missing values. It's important to split your dataset into training and validation sets to evaluate the model's imputation performance. Techniques such as cross-validation can help assess the robustness of the model's predictions. While model-based imputation can be computationally expensive, its ability to capture intricate data relationships can significantly improve the quality of imputation, making it a valuable option for datasets with complex missing data patterns. By using machine learning, you can ensure that your imputed values are as reflective of the actual data distribution as possible.
Evaluating the effectiveness of imputation is crucial to ensure that your chosen methods are preserving the integrity of the original dataset. Visualizations play a key role in this evaluation process. Common techniques include histograms and box plots, which allow you to compare the distribution of original and imputed data. These visualizations can highlight any shifts in data distribution or introduce biases due to imputation. Scatter plots can also be useful, especially when comparing multivariate relationships before and after imputation. Additionally, you can use techniques like heat maps to visualize the correlation matrix, helping detect any artificial correlations introduced through imputation. By iteratively refining your imputation strategies and evaluating their impact through visualizations, you can improve your dataset's quality, making it more reliable for subsequent analysis. This iterative process ensures that your imputation methods are not only filling in missing data but are doing so in a way that maintains the dataset's true characteristics. As we conclude our exploration of advanced imputation techniques in Pandas, let's recap the key strategies we've covered. We explored the differences between simple and advanced imputation, delved into the use of Pandas fillna with complex strategies, and leveraged sklearn's SimpleImputer. We also investigated multivariate imputation using iterative imputer, addressed categorical data challenges, and applied k-nearest neighbors and machine learning models for robust imputation. Remember, the context of your data is crucial in choosing the right imputation method. Balancing complexity with performance ensures that you're not only filling gaps but doing so effectively. Iterative refinement and continuous learning are key as you adapt these techniques to your unique datasets. Thank you for joining this session, and may these advanced imputation techniques enhance your data analysis workflows, enabling more accurate and insightful analysis.